All right. Hello, everybody. Thanks for coming here. Just excited to be talking here about Narrowband IoT. I'm Balaji from T-Mobile. And my colleague, Jeff, will cover both the sort of the business aspects as well as the technical aspects of Narrowband IoT. My objective is to get through the business aspects as fast as possible to turn it on to the technical guy to talk about the more interesting facts, the stuff that you're afraid to ask. So why is Narrowband IoT exciting, right? Personally, I think it's cool because, yeah, first I run the IoT business, and so I like Narrowband IoT because it's got IoT in the name. But more importantly, if you just step back and say, what is the promise of IoT? What is IoT designed to enable? It's sort of this creating a digital representation of the physical world so that we can look and gather information, analyze the information, and act on the information. And in order to be able to do that, you literally need to deploy billions and billions of sensors for you to sense the information that's happening in the physical world. And that's where a technology like Narrowband IoT becomes an enabler, right? Is how do you scalably and more cost-effectively deploy those sensors to be able to gather that information that you can analyze and act on. And so this is probably one of the coolest technologies to come through in IoT that will allow us to get there, that will allow us to fulfill the promise of what IoT is meant to be. So we at T-Mobile have started, well, I guess I'm going to have to click through this, or maybe not. We at T-Mobile started this journey of deploying Narrowband IoT in the summer of last year. There you go. We started with some trials in Las Vegas. We just wanted to kind of test out the technology and see how it works before going on a broader scale. Soon after the trials, we deployed it in a commercial model in Las Vegas in fall of last year, and then started working with the ecosystem vendors, the modules and the chipset vendors in early part of this year to try to build that ecosystem up for this technology. And in the middle of this year, in summer of 2018, we announced a nationwide launch of a Narrowband IoT network. And by nationwide, I truly mean it is nationwide, right? So if you look at the map that we have covered today with Narrowband IoT in the US, that's the one that you see on the left. It covers about 320 million POPs on bands 2, 4, and 12, which is PCS, AWS, and 700 spectrum. And we're not going to stop there because there are still some white gaps to be filled in the middle of the US. And we're continuing to deploy that technology on our 600 spectrum, which we spent about $7 billion acquiring that last year, $7.99 billion acquiring that last year. And that will allow us to go to the map on the right-hand side by the end of next year, which pretty much covers the entire US. So when I say we have a nationwide Narrowband IoT network, it truly means it's a nationwide Narrowband IoT network that you can deploy sensors around the US. What are the benefits of Narrowband, right? I think you saw Chetan and Evan talk about a little bit of this in the session earlier on. One of the key benefits is battery life. As was discussed earlier on, battery life in the realm of 5 to 10 years is not impossible with Narrowband. It depends on the use case, obviously, but that's kind of the range that we expect in terms of battery life. Second is cheaper device costs. Today, one of the biggest impediments in terms of deploying IoT at scale is the cost of a cellular modem that ranges anywhere between $15 to $25. With Narrowband, it's already under $10. And we're aggressively pushing that boundary to get it to a point where it's in the $5 range, such that it becomes very cost-effective to deploy those billions and billions of sensors that I described earlier on in my talk. The third is optimized data usage. Narrowband has this unique way of communicating data using non-IP, which Jeff will get into the details on, which allows you to reduce some of the packet sizes and truly achieve some data efficiency in terms of transmission of data into the cellular network. And last one is enhanced security. This being a GSMA standard, SIM-based authentication running on licensed spectrum, it's probably more secure than any other forms of communication modalities available to solve for these use cases. So those are, at a high level, those are probably the 4 biggest benefits that you see as you go into Narrowband IoT space, and that's what is going to enable true scalability and deploying it to several sensors to be able to achieve the promise of IoT. So what are the use cases? I just want to touch on a few high-level use cases. Smart buildings, of course, I mean, as you think about buildings, as you think about the thermostats inside the buildings, as you think about lights inside the building, and at some point down the road, hopefully soon, those will be directly connected to the network. There's no reason for that to go through a Wi-Fi network. It introduces several inefficiencies in that. And I mean, I bring up my personal example. I have lots of devices connected in my house, and it is a pain. It is a pain to have the device talk to a gateway, the gateway talk to a Wi-Fi router, the Wi-Fi router then talks to the internet. It just introduces additional points of friction and additional points of failure, to the point that, I mean, my favorite example is when, at one point in time, several months back, when my power went out and the power came back on, for some reason all the lights in my house started blazing, and I couldn't talk to any of the lights through Google or Alexa because the Wi-Fi connection was not up by that time. So I had to wait for a full 5 or 10 minutes before I could establish that connection, and that was really painful. I was about to lose the license to experiment inside my house. So that is the promise of Narrowband IoT. What can it do? It can directly connect to those devices, directly connect to those endpoints, so that you don't need to go through those points of failures and points of potential friction that exists between taking data from the device and out to the cloud and the internet. Asset tracking is another example that we see a lot, and smart waste management, smart parking, those are all the typical use cases that we're seeing in the Narrowband IoT space. And actually, I've run into some very, very interesting use cases as well. For example, I was visiting Southeast Asia, and one of the carriers have deployed a Narrowband IoT-based dash cam, and I was curious. I mean, that's not the use case that I would think of when I think of Narrowband IoT, but apparently, if you just transmit a static picture of who bumped into a car at the time the car was bumped into, the payload is so small that you can use a Narrowband IoT network to transmit it. It's infrequent, and a small payload can still be done with it. So, and that is why we are excited about the announcement today with Twilio, because we don't know what those exciting use cases are, and we want to get the technology as technology enablers out to the developer communities, such as yourself, so that you can start working with the technologies and try to drive adoption of these use cases in a mass scale in this market. So that's the boring business talk. I'm going to give it to the exciting technical guy now.
Thanks, Balaji. Yes, my name's Jeff Harmon. I work for the Technology Development and Strategy team at T-Mobile. And I thought I'd begin the technical talk with a bit of an evolution of IoT in general. So there's a lot of words, a lot of detail on this slide, but as we move from left and right, the first three categories, I guess, on the left are what we like to call 3GPP categories, or Third Generation Partnership Project. This is the telecommunication consortium that carriers like T-Mobile adhere to from a standards perspective. So we began all the way back with LTE Category 1, which is a few years ago. And the idea was to remove complexity of devices by reducing things like bit rates. This particular device, from Category 1 perspective, is still a full bandwidth device. However, we could still get reduced cost, and we had the ability to run the Category 1 devices on our network, on our licensed spectrum as well. But the smart people at 3GPP then decided to, in Release 13 a couple of years ago, develop LTE-M and NB-IoT. And they're the two that you see next in line. As we go to LTE-M, we further reduce the complexity of the device by, again, reducing the bandwidth down to about 300 kbps. So we've gone from Mbps, or megabits per second, down to kilobits per second. And we've also changed the mode of the device to be half duplex. That means we can't send and receive data at the same time. And we've also reduced the bandwidth of the device down to 1.4 megahertz. And as you can see, the relative modem cost also drops, and we've also reduced the battery life. However, LTE-M needs to reside on an LTE carrier. So we thought, well, what else can we do? So we invented NB-IoT. NB-IoT, again, further reduces the complexity of these devices down to tens of kilobits per second. It's also half duplex, but you'll notice that it's running on a 200 kilohertz carrier, which is a lot smaller than the LTE-M carrier. And also, the device cost is further reduced, and the battery life goes up to, as Evan said today, up to about 10 years. You'll notice that the last row down the bottom also touches on coverage and what the coverage improvement is. I'll talk about that a little bit later in the slides with the feature introductions. And you'll see that there is an increase in coverage using NB-IoT. The two technologies to the right are what we call sort of non-standard, non-3GPP standard technologies you would have heard about, LoRa and Sigfox. You can see that they are also reduced complexity devices, reduced cost, low cost, and also reduced bandwidth devices, down again in the kilobits per second. I'm being nice to Sigfox here. It's really in the bits per second. That's how small we're going with Sigfox. But the one key difference here is that they're running on unlicensed spectrum. So what does that mean? What does that mean for you? What it means is NB-IoT not only can run on T-Mobile's licensed spectrum and network assets, so radio cell towers that we have existing today, but it can also meet the demands of the low complexity, low cost, low power, long battery life, long device cycle devices that are being addressed by using LoRa and Sigfox. So NB-IoT has its benefits for everybody, and by doing this we can launch a nationwide NB-IoT network with simple software upgrades on our cellular radio network today. So how do we do that? So with NB-IoT there's 3 modes of operation, 3 deployment modes. We have in-band on the left. In-band's okay, it's a good solution. It sits within our existing LTE carrier network. But what that means is sort of the equivalent of, to use the road analogy, the highway analogy that our team likes to use. It's like running push bikes on a highway. So how can we improve that traffic flow? We move to guard band technology, which is in the middle, and that's our preferred mode of deployment. And by moving to guard band, what we actually do is we can shift the NB-IoT carriers to currently unused spectrum that was guard bands were deployed and they're actually over-dimensioned when the LTE began. And there's actually, I guess, the equivalent of, say, 5 lanes on either side of an LTE spectrum carrier where we can actually fit NB-IoT carriers in. So we can deploy NB-IoT carriers within our existing licensed spectrum on either side of our LTE carrier without impacting traffic on that LTE carrier today, which is used by smartphones that everybody uses. One of the benefits here, again, is we get to use our existing cell towers and our existing spectrum assets. The last one is standalone. Standalone is a nice deployment option. However, we may need to deploy new radio equipment to run this technology. So again, we can use this technology, and we have a little bit more coming in maybe in the later or the earlier parts of next year, which we might use standalone, but preferred mode of deployment for T-Mobile is guard band deployment. So some fun and new features that NB-IoT brings. So we'll talk about coverage enhancement. I touched on it in the first slide with the 10 or 20 dB of coverage gain that we get from NB-IoT. So how do we do that today? Well, NB-IoT introduced is something called coverage enhancement modes. So we have 3 levels of coverage enhancement, levels 0, 1 and 2. And what it does is based on the device's radio conditions, so where it is in the network, the device will actually select a level of repetition that it can use to further increase the probability of traffic to go through. So it is dynamic, it's quite flexible, and once the device is actually connected using these repetitions from a semi-static environment initially, it turns into a more dynamic experience as the session is continued on. So what that means is if a device is actually in good RF conditions, doesn't need to use repetitions, it won't actually do that. So, and as you can see here, the theoretical gains that NB-IoT and in 3GPP again have stated is up to 20 dB of gain. So what is 20 dB of gain? It's actually a tough question to answer, but we equate it to effectively, instead of hitting, say, level 1 of a car park, you might hit level 3 of a car park. Instead of maybe entering just coverage of an elevator lobby, you actually get into the elevator itself and things like that. So it can make quite a difference for IoT applications. So, what about battery life? Now again, quite a busy slide, but we have something in NB-IoT called power saving mode and extended discontinuous reception, which is quite a mouthful, but we'd like to call EDRX. So if we just focus on the left-hand side of the slide, I'll go through power save mode. So how does power save mode work for NB-IoT? Essentially, the device and the network negotiate what's called their duty cycle. So some use cases, as you will know, in development, will require longer duty cycles than others. The device may only need to wake up once a day, once a week, once a month to send data or monitor for incoming data. So we have the ability at this point for the device to tell the network, I only need to wake up once in up to 310 hours. So during that time, it sends its data. It will monitor for a little while and then go into what's called a deep sleep state. In the deep sleep state, it's effectively disabling the modem almost at that point, and we're getting into what's called roughly microamp current draw at that point. And you can see with microamp current draw, we can actually extend the battery life of the device substantially. Once the duty cycle is finished or the timers are up, the device will wake up, monitor for data again, or send any data that it needs to send, and go back to sleep, and then the cycle repeats. EDRX, slightly different. It's used for use cases which maybe don't need months or weeks, and maybe need hours. So the device will, again, go into its cycle and periodically wake up and monitor for traffic on the downlink, as noted by sort of the shorter magenta spikes. If there's no traffic for it, it will go back to sleep. It's not a deep sleep state. It's not quite microamps, but we're working on that. And then in the next cycle, it'll continue again. And it'll monitor for downlink data or send uplink data if needed. And this is use case specific again, and we can trigger up to 2 hours, 55 minutes, or roughly 3 hours for a duty cycle of EDRX. So we can't do this effectively with some, you wouldn't want your smartphone acting this way. If people are trying to make a call to you and your device is in deep sleep, that wouldn't be very efficient. So we do this with IoT devices in particular. So with these two features, we can greatly extend the battery life of our devices. But there are trade-offs. Now, I know you've seen this slide. If you went to Evan's session previously, you're going to hear it again, just in a little bit, I guess, just a better accent this time. So there are trade-offs. With increasing coverage, obviously with more repetitions as the device is active longer, your battery life will decrease. And also with device duty cycle, so as the device needs to wake up more often, it will also decrease the battery life. So a couple of points. Increased coverage, as I just stated, decreases battery life. But it also means that smaller payloads that are sent more frequently will decrease battery life. So how do we reduce the payload of a data transmission? And we do that by focusing on data connectivity and data delivery, which becomes really important. So data delivery to reduce overhead. So how do we reduce overhead? There's two ways. There's transactional overhead, and then there's IP overhead, which is on the top. So by removing IP and TCP headers, things like that, which really dominate the transmission when you're talking about 5 or 10 byte transmissions. By reducing that overhead, we can greatly reduce the actual transmission that's being sent over the air. And secondly, the transactional overhead. So we like to use TCP. It's robust. IoT protocols such as MQTT are based on TCP. But they include three-way handshakes at the beginning of a session and also teardowns. And effectively, these transactions are actually overhead. So at T-Mobile, we prefer what we call transaction light-based protocols, things that are based on UDP or things that have no IP headers at all, say NIDD. The next slide we have is, this is a study that was done by DT in Germany, our parent company. We did a similar study here. This was just a much nicer looking slide. What we found is that on the left-hand side, we have what's called publish-subscribe based protocols, and on the right-hand side is REST-based protocols. But the point of this slide here, really moving from left to right, is to show the impact of non-IP UDP traffic and versus, say, TCP. And we found that TCP is very chatty, and it's also payload heavy. And you can see how the payload of what you're actually trying to send, the valuable data, is really small when it's put next to the header sizes of, say, MQTT and TCP as an example. And on the right-hand side, again, when we use CoAP or UDP-based transmissions, you'll see that the overhead is reduced. And what we actually found with non-IP data delivery, which is coming shortly, is that we can save up to 10 extra transactions for a 5-byte transmission for TCP or MQTT protocol transmissions. We can also reduce the payload up to 100x for a single 5-byte transmission. And this is significant, again, when you're looking at a $4 rate plan, in the scheme of how NB-IoT works. So some things to keep in mind when we're developing programs and applications for NB-IoT, and IoT in particular. So I'll discuss a little bit about NIDD now, or non-IP. In addition to removing IP headers, NIDD as well also reduces the need for IPs at all. So in general, the devices will register on T-Mobile's network with the device ID. And what actually happens as well is the application servers at the other end are registered on T-Mobile's network as well. So only authorized transmissions can happen with a non-IP device to a server. And how is all of this done? Through APIs. So we increase security by removing IP addresses, and we also authorize only communication from certain servers to the devices. So you can see how non-IP, as it grows, will increase security as well as reducing payload and also overheads for data transmissions for IoT. So what is the end goal? We've been through extended coverage and what it does for you, and it's fantastic. It can give you deep indoor coverage throughout the network today. But we need to think about how often we transmit our data to our application servers as well. So we need to keep in mind how often we're transmitting and also what the impact of battery life is. So we're looking for a sweet spot in the middle. So we're after, in a nutshell, infrequent small payload sizes over IoT. So with that, NB-IoT can offer years of battery life, improved coverage, but it also just implies that payloads are small and infrequent, and we need to keep that in mind when we're developing our IoT applications. So that brings us to the Narrowband IoT the test kit and development kit that you have, hopefully all of you have picked up, and the partnership that we have with Twilio today. So with that, are you with us? So hopefully we can all develop some IoT applications moving forward and change the world. So thank you.
Does anybody have any questions for the T-Mobile team? It's kind of hard to see in here, but I'll try.
No questions? Not even from the front row? Nothing?
Nope.
All right. Well, thank you everyone again.
Thank you.
Oh, there's one here. Okay, sure.
Talk more about security of this whole thing.
Security is an interesting one. Inherently, security exists with network deployments today. Out of the box, we have SIM card security, session security over the air. And then also, I think, as far as Twilio, the APIs are concerned, I think they have security built in as well. I'm looking over to colleagues here who are more familiar with the kit. So end-to-end, there will be security built in, especially with NIDD as well, as they register with our servers. With the standards, it'll be TLS, one of those versions, Brunema? Okay. So there will be added security on top of the inherent security that's already there with cellular networks today. So, yeah. That was it, sorry. Yep.
Anything about pricing models? Like what do you say about pricing plans?
I'll give that one to Balaji.
Well, I think we did announce, as a part of the Twilio release, we announced certain pricing plans that's in the Twilio website as you go into Twilio and leverage their APIs to talk into our Narrowband IoT networks. I think those pricings are published. It's at scale, I believe it's $4 a year, and it starts at $8 or something like that, but it's published.
Over here. You mentioned that devices are whitelisted on your network to jump on the network. Is traffic that come from those devices, is that encrypted end to end, or do you guys like decrypt before you communicate to your APIs?
So end-to-end decryption application will be, I guess, use case specific. So that'll be up to the developers at that point. So, I mean, over-the-air encryption happens again with LTE networks, right? So that's a different type of encryption, but the application encryption needs to be done end to end at this point. So, yeah.
I was wondering if you could talk about data latency from when the device connects and sends its packet over. You know, what's the expectation of? You said small and infrequent, but when it does come, what can I expect?
We do expect an increase in latency. So the preference is to have latency tolerant, I guess, applications is what we like. That's the term we like to use. And you know, it can be anywhere from probably seconds to tens of seconds, depending on your radio coverage, as I pointed out. So as you have things like coverage enhancement modes enabled, and again, the other cost is battery life, but it's also latency, because if we're sending up to 2,000 repetitions of the same thing, obviously that takes time. So that'll increase the time for packets to be sent and packets to be received as well. So somewhere in the order of seconds to tens of seconds. Yep.
And just a quick follow-up, is it also considered like a best effort service?
We'll call it a carrier grade best effort service. How about that?
I can live with that.
You can live with that? Okay. And that's the key component as well, because it's running on a carrier grade system. So licensed spectrum, nationwide cellular network, everything that we run at T-Mobile today.
Yeah, and usually our networks are pretty reliable. They don't go down.
Yeah. Anything else? Thank you very much, everybody.
Thank you.
Enjoy.